Swayam Prabha. Digital India. Educated India.
Welcome back. Today is the lecture 4 of this course, Aerodynamics and Performance, faster than Schindelic. In the last class, we discussed about the significance of aerodynamic center and how aerodynamic center location is preferred over center of pressure. So in today's class, we'll be deriving the relation between the center of pressure and the aerodynamic center. Alright, so let us go ahead. Relation between center of pressure and aerodynamic center. As usual, I will be drawing a cambered airfoil. Okay. This is the chord line. This is the chord line. This is the leading edge. Now, this is the aerodynamic center, which is generally closer to the quarter chord point. So, this is aerodynamic center, AC, and this is the center of pressure. Center of pressure. So, if we are considering the forces here at aerodynamic center, this is the lift L, and here will be also be having moment above aerodynamic center. And if you consider forces at center of pressure, there will only be forces, there will not be any moment, as we discussed in the previous classes. So, this aerodynamic center is at a location of XAC from the leading edge, and center of pressure is at a location of XCP from the leading edge, always from the leading edge. Alright, so please do not get confused. We always measure from the leading edge only. Alright. So now considering center of pressure, first we will consider center of pressure. Okay. Then moment about leading edge. If you consider center of pressure, then how can we write moment about leading edge? Moment about leading edge is equals to, now this will be minus L into XCP. Okay. This is minus L towards this leading edge. This is will be negative moment. So minus L into XCP. This force, this is the force, and the distance is XCP. Alright. So this is actually pitching downward. So this is minus XL into XCP. I hope that is clear. Now considering aerodynamic center. So again, moment about leading edge. So we are considering same reference point, leading edge. Alright, since we are developing the relation between the CP and AC. So now moment about leading edge is given as, the moment about leading edge equals to minus L, this is minus L into XAC, this is the distance, plus this time there will also be a moment about aerodynamic center. Alright, moment about aerodynamic center. Now let us consider this as equation 2. So since both moments are same, hence equating one and two. We are equating this 1 and 2. Alright. So let me write here minus L into XCP. I hope you are noting down the point. Minus L into XCP minus L into XAC alright, plus MAC. Now again we'll be doing here the same, that is dividing by QSC on both LHS and RHS, so that we can get rid of these magnitudes, lift L and moments M. Alright, so minus L by QSC, I'll write XCP upon C rather than QSC. Okay. Similarly, minus L by QS XAC by C plus MAC upon QSC. Alright. So this can be written as, we know CL equals to L upon QS and CM equals to M upon QSC bar. So we can write here minus CL, and I am denoting this by bar. Remember, bar was, what does the bar indicate? That this is a non-dimensionalized parameter with respect to chord. Okay. So minus CL, again minus CL XAC bar, that is the non-dimensionalized with chord, and here we have CMAC. Okay. Now finally we can write XCP bar equals to XAC bar minus CMAC upon CL, minus CMAC upon CL. Now let me just put it in a box. Now if you focus on this equation carefully, what we note here, the CL is actually at the denominator. Okay. And remember, the CL versus alpha curve, as the angle of attack is increasing, then CL is also increasing. Okay. So at higher angle of attack, CL increases due to the linear relationship. That means, hence, CMAC upon CL quantity decreases. Alright. And then what happens if this is decreasing? What happens if this term is decreasing? So that means your center of pressure is approaching towards the aerodynamic center. Okay. Aerodynamic center is a fixed point. Please remember. So here as CL is increasing, so center of pressure is approaching aerodynamic center. Alright. Now let me just, in the last class I was also mentioning about something related to positive cambered airfoils. Positive cambered airfoil. So as of now we have discussed the cambered airfoils. So let me draw the cambered airfoil. So this is the chord line and this is the mean camber line. So here mean camber line is actually above the chord line. Okay. The mean camber line is actually above the chord line. So if mean camber line is above the chord line, then we call it as positive cambered airfoil. Okay. And if the mean camber line is below the chord line, then we call it as negative cambered airfoil. So what happens with this positive cambered airfoil is, since we have asymmetric pressure distribution because of the curvature of this airfoil, here we have higher force at the bottom. This is larger force. Alright. And this is a smaller force. This is a smaller force. So then what happens? So this let it go. This is equivalent to this is considered as aerodynamic center. So here we have net resultant force F, resultant or total force. Alright. Remember, for the positive cambered airfoil, it was even producing lift even at zero angles of attack. And here we have higher pressure at the bottom surface. So here we have resultant force at the bottom surface. Okay. So this is again equivalent to, this is the aerodynamic center. So because of this force about the aerodynamic center, it will produce a nose down pitching moment about aerodynamic center. That's why CMAC is always negative. It first of all exists and is negative. So for this was applicable for positive cambered airfoil. So what will happen for negative cambered airfoil? Just remember the opposite. Here will be having, although CMAC will be existing, but will be positive. We rarely use negative cambered airfoils. Mostly we'll be using the positive cambered airfoil since we need a positive lift even at 0 degrees angle of attack. Alright. What about symmetric airfoil? I have discussed this before. So let me just refresh your memories. So here what happens is, this is the symmetric airfoil. Alright. So here exactly at one point, this will be 1/4. Exactly at the same time, this will be another force which will be acting at a point. This will cancel out each other. So pressure distribution over the top surface and the bottom surface after integration acts at the same point, and hence there is no couple. Remember CL versus alpha curve? It was actually starting from alpha equals to 0. So there is no couple, there is no moment. Okay, and there is no lift at alpha equals to 0. That is CL at alpha equals to 0 equals to 0, and CMAC will be equals to 0 for symmetric airfoil. So please remember this point, that CMAC will be 0 for symmetric airfoil and it will be existing for cambered airfoil. Okay. Now coming for, so similarly if you see this equation, so for this symmetric airfoil, this equation reduces to, so for symmetric airfoil, so XCP equals to XAC bar. Alright, since CMAC itself is 0. Okay, so please remember this point. Now let us demonstrate this with an example. Consider an example. So consider a Cessna 172 aircraft. So Cessna 172 aircraft is a lighter aviation aircraft which looks something like this. So this is the Cessna 172 aircraft. Alright. So let me denote the parameters of Cessna 172 aircraft. Here weight of the aircraft is 1000 kg. Suppose the aircraft speed is 50 meters per second. Area is 16.2 meters square, and assume the aircraft is lying at the sea level, that is density is 1.225 kilogram per meter cube. Chord length is 1.5 meters. Okay. Consider NACA 2412 airfoil. where CMAC is, it will be what, positive or negative? It will be obviously negative, minus 0.05. Okay, so CMAC will be negative. This is positive cambered airfoil, minus 0.05. Now the question here is find the CP location. Alright, so we will be solving this both here in the notes as well as in MATLAB. So that will briefly introduce you to the MATLAB software in today's class. The CP location, as we know, it is given as XCP bar equals to XAC bar minus CMAC upon CL. So now XAC aerodynamic center, we know it is at quarter chord point of the chord 0.25 into C. So the chord length is actually given to us. So 0.25 into C. C is nothing but 1.5. So what you get here is 0.375 meters. Please do not forget to mention the units. It is 0.375 meters from what? Leading edge or trailing edge? Obviously from leading. Alright. You can also mention in non-dimensionalized form XAC bar equals to 0.25. So which we are already aware of. Alright. Next, we already know the lift equation, coefficient of lift equation, CL equals to L by QS. Okay. So that we'll assume the aircraft is flying at steady level flight. Steady level flight. Steady in the sense there is no acceleration. Level in the sense the wings are level. Alright. We'll assume it is a steady level flight where actually lift is exactly balancing the weight. Okay. So here steady level flight we have L equals to W. So CL you can mention here W by QS. Okay. And W by Q we know it is half rho V square S 2W by rho V square. So 2W by rho V square S. So we'll simply substitute the equations over here. So 2 into 1000 divided by 1.225 50 square multiplied by 16.2. So what students will do, they will simply substitute these values and try to obtain this CL. Now remember the dimension of the CL was unitless. So we need to have this dimensionless coefficient. Now what is the unit of weight? Here if the weight is actually given is 1000 kgs. So we have kgs in the numerator, that is actually the mass, not the weight. So kilogram divided by the unit of density is kilogram per meter cube. Alright. Velocity is meters per second. So meter square per second square. And the area is meter square. Alright. So we know the dimension of this is unitless. So if this kg goes, so in the numerator we have, this is meter power 4 meter cube. So in the denominator will be having 1 meters per second square. So did it vanish? No. So this method of finding CL is actually wrong. Okay? The reason is you have to convert this unit from mass to weight, that is to Newton. You have to multiply this by 9.81. So most of the time students will do this mistake of not converting the units. So whenever you have any confusion that what unit to use, blindly just write the units of left hand side and right hand side equation. If they are matching, that means you are sure you can use those expressions or those units. If they are not, then definitely you have done some mistake. So most of the students will commit mistakes here in converting to the desired unit. Alright. Now let us See, if you convert it to weight, then are we getting the CL dimensionless or no? Let us try again. So 1000 kgs, so kgs into, you multiply by 9.81, you will get meters per second square. Denominator is, we are getting density is kilogram per meter cube. The velocity is meters per second, so meters square per second square, and here the area is meters square. So this kilogram goes, alright, this second square goes. So here we have meter power 4 divided by meter power 4. So finally it has become unit length, which is actually correct. Okay, so please check the units before inputting the value. Alright. So now finally we get CL equals to 0.3954, approximately 0.3954. Okay. Now let us find XCP bar. You have x 0.25, that is AC location, 0.25 minus 0.05, that is actually given, divided by 0.3954. So this you are getting approximately 0.3764. Alright. Now if you want to obtain here in terms of exact dimension, so XCP bar is what? XCP by C. So XCP equals to XCP bar into C. So equals to 0.3764 into 1.5. So 0.5646, approximately 0.5 meters. Okay. So let me write here what is the result. So let me write here what exactly does this mean. So this means that and CP is around 56 centimeters from the leading edge, which is aft of aerodynamic center. Where was aerodynamic center? Quarter chord point, right? So 37.5 centimeters from leading edge, which is as expected for cambered airfoil. Alright. Now there is another point. As CL is increasing, the CP should move towards aerodynamic center, so which we will be showing from the MATLAB plot. Alright. So let me quickly go to MATLAB now and demonstrate this result. Alright. So I have written, now this is how the MATLAB window looks like. On the left hand side we have the files or the working location. Below is the command prompt. Okay. And the right side I have the workspace. So whatever variables I am defining, it will be appearing here in the workspace on the right side. Okay. Now I am writing the code over here. Okay. Edit script. I open here new open script. Okay. So this is the script, new script. CLC will actually clear this command window. So before writing any code, I usually write these commands. CLC will clear the command window. Clear will clear all the parameters defined in the workspace, and close all will close all the figures if any figure is open. Alright. So now let us write the code. The percentile sign will indicate that I am writing the comments. The MATLAB will not implement those. Those are the comments for us to read. So the aircraft parameters. Now I will be writing the comments, the parameters. mass equals to 1000, and then I'm ending the quote with a semicolon indicating that this is the quote, or this is where it should finish, the line is finishing. Or even you can continue from here itself. You can mention here G equals to 9.81. Okay, then this parameter is done. Then we have density. Let me write density equals to 1.225, which is kilogram per meter cube. Alright, next we have W. W equals to mass. We know W equals to mass into gravity. Okay. Then area is given, S equals to 16.2 meters square, and chord is given. Let me denote it by C itself. C equals to 1.5 meter. Okay. Now next, the aerodynamic parameters are given, which is okay. So this comment is for us, for our understanding. So let me write CMAC equals to minus 0.05. Okay. Next XAC bar. Next AC bar. Notice how I am writing the underscore over there to define the values. XAC bar equals to 0.25. Okay, the location of the XAC aerodynamic center, that is bar, non-dimensionalized, directly it is 0.25. Then I will define the velocity, defining the range of velocity, defining the range of speeds, rather defining range of air speeds. Alright, so let me define the range as from 30 to 70 meters per second, that we can use linspace command from 30 to 70 meters per second, and I will divide it to 100 points. Okay, so it will enter 30 to 70 meters per second divided by 100 points. Alright, next we will be finding the lift coefficient. CL equals to, I'll mention here in brackets, 2 into W divided by rho V square S. Rho into V square into S. Alright. Okay. Let us see if it is running or not. So here we have an error over here. This happened because the V is a vector over here. In the workspace we have a V, this is a vector of 100 elements. Alright, so this is a vector of 100 elements. Let me close it down. So we need to do element to element multiplication or division. Alright, so since W is scalar, rho is scalar, S is scalar, but V is a vector. Alright, so we need to do element to element multiplication or division. So that in MATLAB we can incorporate, before the operator you have to mention here dot. Okay, similarly before the operator here you have to mention here dot. Alright, now if I run this code, and now there is no problem. Okay, fine. Now let us go ahead. Now that we have calculated CL, now find XCP bar. XCP bar equal to XAC bar minus CMAC upon CL. CMAC upon CL. Now even here CL is a vector here. Okay, so we need to mention here dot. XAC bar minus CMAC upon CL. Alright, now we can convert this to dimensional XCP. Fine. So XCP equals to, instead of bar, I will simply write XCP equals to XCP bar into the chord or C that I mentioned before. Alright. Now quickly we'll be plotting the plots. First, let us denote the figure 1. So I'm writing this code from the scratch so that it understands each and every line. What am I doing or why am I doing? Alright. So we'll plot x versus y axis. In x axis we have CL, comma. In y axis we have XCP bar. XCP bar. Okay. Now x and y axis is done. Now I'll denote at how I want to. Just a second. Let me denote it by B, the color of the line, and even we can mention the line width also. Line width, comma, line width, comma, line width should be approximately 2, not approximately, it will be exactly 2. Now what do you want in the x label? I would like to mention in x label, please write lift coefficient CL. Lift coefficient CL. Alright, and always ending the code with line with a semicolon. Then what do you want to write in label? Y label. Then Y label will be mentioning what is in the y axis? Non-dimensional XCP. Okay. XCP by C. XCP by C. You can also mention title over here. The title I am mentioning center of pressure versus coefficient. And with varying speed. Alright. Okay. I'll keep the grid on. So that can be really highlighted. Legend, I'll mention it as XCP by C. CP by C. Alright. I think more than sufficient. Let me just select all and run it. Yeah. And this is the plot that we are getting, XCP by C with the lift coefficient CL. Alright. So I can, L should be in the denominator. It can be written in this way, C underscore L. Alright. This X, even this one, X underscore CP, and then curly brackets. Alright. Alright. So now making sense, right? So now let us check this equation. Now what we calculated at CL equals to 0.4, right? So CL equals to 0.4, approximately 0.39. So XCP by C is 0.375 meters. So we also got the similar result. Okay. So as you can see, as CL is increasing, this CP location is actually going towards the aerodynamic center location. Okay. And you can also plot it between directly without the non-dimensionalized parameter. You can mention here figure 2. Let me just copy so that Alright, so figure 2. In figure 2, we'll be having the CL with XCP. It will not be bar. Alright, let me denote with the red letter. Lift coefficient with dimensional XCP. XCP, there will not be any bar. And this will be in meters. Alright, center of pressure in meters versus lift coefficient. So XCP in meters. Alright. Now let us run this code. So this is figure 1 that earlier we have drawn, and this is figure 2. This is directly written in meters. So as the CL is actually increasing, so this CP is actually moving towards the aerodynamic center. So that was the whole point of showing in MATLAB. Alright. Now let us move to the next topic. Now let us quickly move and discuss about the airfoil, different types of airfoil drags, and what exactly do you mean by finite and infinite wings. Alright. So in many textbooks on literature, you must have heard or seen the concept of finite and infinite wings. Let us discuss about that. Okay. Airfoils, airfoil drags, and concept of finite and infinite wings. So due to the presence of friction, there exist two sources of drag. Okay. Due to the presence of friction, there exist two sources of drag. So let me write out the first one. The first one is the skin friction drag. Skin friction drag due to the shear stress at the wall. And the second type is obviously because of the flow separation. So there will be drag will be generated. That drag is nothing but pressure drag due to flow separation. Alright, pressure drag due to flow separation, and this we also call it as form drag. Okay, so let me write down here CD equals to CDF plus CDP. Okay, CDF is skin friction drag and CDP is the pressure drag. Now, if you even consider for supersonic speed, for supersonic speed, then obviously there will be shocks, and then there will be another type of drag, that is wave drag. Okay, so then we add another one here, that is CDW. So as of now, this course deals about with the subsonic flow. We will consider this wave drag to be equals to 0, and we will write CD equal to CDF plus CDP. And if you notice this carefully, so these two are because of the shape and size of the wings or the body or the aircraft body. Okay? So this CDF and CDF is also known as, combination of these two is also known as profile drag. Alright, so I have taken names of form drag, profile drag, wave drag. Alright, we are ignoring wave drag as of now since we are discussing about subsonic aircraft. So CD equals to CDF plus CDP. Alright, and let us go ahead with this assumption. And one more thing, in the wind tunnel testing, let me write here. and even draw a figure before I go further. So in wind tunnel, consider this is a wing. Alright. So in wind tunnel, we assume this spans from plus infinity to minus infinity. Alright, this is the velocity in this direction. This is the x, and this is the y. And where will be the z? If x is this direction, y is in this direction, z will obviously be downward direction. Okay. So in wind tunnel, we assume it is always 2D flow. That means the flow is moving only in x direction, okay, and in z direction, but not in y direction. There is no sideways motion, no side velocity. Okay, so we always consider motion to be a 2D flow in the wind tunnel, and in the wind tunnel, this test model is spanning the complete from the left of the wind tunnel to the right of the wind tunnel. Alright, that is from plus infinity to minus infinity. That's why we consider this one as 2D flow or infinite wing. Infinite wing in the sense, infinite wing in the sense, what? What do you mean by infinite wing? That means there are no wingtips. Alright, but obviously for the real aircraft there will be wingtip, but for the experimental result in wind tunnel we assume it is as an infinite wing. So whatever the results that we have obtained, CL, CD, CM, for the different angle of attack, so those results were valid for only infinite wing. Okay, fine. Now obviously the real aircrafts, they are finite. Now consider this as a left wing tip and this as a right wing tip. This is the velocity, free stream velocity. This from complete left hand side, starboard to the port side, this is nothing but the wingspan. And we denote it by a small letter b. So as soon as we know this wingspan b, we know the wing area s, we can actually calculate the aspect ratio of the wing. Aspect ratio is given as square of the wingspan, b square upon h. Alright. So I have started denoting this parameter since this will be useful in the coming expression. Alright. So aspect ratio is b square upon the wing area. And will this have any unit? Obviously, no. It's dimensionless. B square by s. Okay. Now flow about finite wing. Flow about finite wing. That means wingtips obviously are existing. Those I'll denote the coefficients as capital letter CL, CD and CN. Please do not get confused with this abbreviation. Alright. So for 2D flow infinite wing, I am denoting the coefficients as small letters CL, CD and CN. For finite wing, I am denoting the coefficients as capital letters CL, CD and C capital I. Alright. Now, I often ask this question to students. So if you consider a NACA 2412 airfoil, NACA 2412 airfoil, okay, and if I tell you to do wind tunnel experiment for at alpha equals to say 6 degrees, alright, and you did the whole hard work and finally found the plots between CL versus alpha curve, and what you got was CL equals to 0.85 and you got CD equals to 0.077. Alright. Now my question to students would be, so this was applicable for infinite wing for a 2D flow, but obviously we are having a finite wing, there will be wingtips. So what do you think the lift 3D lift coefficient will be equal to 0.85 and CD equal to 0.077. Will this be same? That is the question I generally ask students. Alright. So what do you think? Will this remain same or no? So answer is actually no. It will actually change. So what happens is, now consider this as a front view of the wing, and as I said you, there will be higher pressure at the bottom surface and there will be low pressure at the top surface. Alright. So as the flow is going from even at the wing tips, there is a tendency for the flow to escape from here. That is, the flow will escape from the higher pressure region to a lower pressure region. Alright. So this flow establishes a circulatory motion. This flow establishes circulatory motion that trails downstream of the wing. Alright. And this trailing circulatory motion is called as circulatory motion is called as vortex. Alright. So you must have heard about the vortices around the wingtips. So these are vortex. So let me quickly show you an image of this vortex. Now see the image over here. Now can you see the circulatory motion which you can easily be observed from here, and see the circulatory motion over here. So these are nothing but vortices which are created downstream of the aircraft. Alright. So this is because of the trailing vortices which is created at the tip of the wing. Alright. Okay. So now these wingtip vortices will induce, because of the vortices, these will induce a small downward component of air velocity. Downward component of air velocity in the neighborhood of wing. Alright. So there we have a downward component of air velocity in the neighborhood of the wing itself. This downward component is known as is called downwash. It is usually denoted by small w. Alright. So let me draw a figure again over here. So if the flow velocity was in this direction, that is free stream flow velocity, but when the aircraft actually reaches towards that point, so then the velocity direction will no longer remain in this direction. It will actually be inclined. It in fact tilted downward. Alright. By how much? By a downward component W. Alright. And now this is the local flow. Local flow in vicinity of wing. Now you understand why we generally denote far upstream velocity as v infinity, because here when the flow is near the body, the flow is no longer remains the same as it was far upstream. Now the flow is actually inclined. In fact, downward, because of downward component of velocity is inclined by this angle. Alright, and this angle is known as induced angle. Induced angle of attack. So because of this induced angle of attack, your actual angle of attack has actually been reduced. Alright. Hence, we can say for a 3D wing, the first effect is alpha is effectively reduced. And the second, because of the vortices, there will be increase in the drag. There is an increase in drag and is called induced drag. So remember, I have told the names of form drag, profile drag, and now we have induced drag, which is created because of the lift creation. Now the question that I asked you was, will the CL remain same? Now can you answer this? Will CL remain same as small cl? Obviously answer is no. Okay, because the angle of attack is reduced. Remember the relation between CL versus alpha curve? Now your effective angle of attack is reduced. Now your lift coefficient will be reduced. Now what was the value that I have mentioned here? So CL will no longer be 0.85. It will actually, CL will be less than 0.85. Okay. Now what about drag coefficient? 0.077. The second consequence was that there will be an increase in drag, that is induced drag. So now your CD will actually be greater than 0.077. Alright. So now I can mention this point. So total drag can now be written as let me write here capital D now, CD, and this is small d plus induced drag, CDI. So this CD small d is profile drag and this is induced drag. Okay. So this induced drag can actually be calculated. So I always tell students, if there is a lift, then there will be induced drag. Okay, so nothing is free in this life. If there is a lift, then there will always be an induced drag. Okay, so now total drag is actually CD equals to CD plus CDI. And this induced drag can actually be calculated. Okay, so there is a method for calculating induced drag as well. Let me just draw another figure over here. Okay, this is the chord line. Alright. Now this is the V infinity and this was the angle of attack. So now actually your angle of attack is reduced. Let me denote this one as alpha g now. Alpha g is geometric angle of attack. So now previously V infinity was in this direction, but now because of the downward component of velocity, your local flow will be in this direction. Okay, what is this? This is local flow. local flow or local relative wind. Fine. And this has been reduced by the angle of attack, that is induced angle of attack. Okay. This is induced angle of attack. Now effective angle of attack would be what? Now finally this much, this is actually your effective angle of attack, alpha EFF. Effective angle of attack. So previously alpha G equals to alpha I plus alpha effective. Alright. So now your alpha effective is alpha G minus alpha I. Okay. And here we have the lift component. This is the lift component. Now please note that this lift component is no longer perpendicular to the V infinity. Okay, so this L is now perpendicular to this local relative wind. By how much? By alpha I. Okay, and this is the DI, induced drag. Okay, now we'll continue from here from the next class. As of now, you ensure that you remember this figure or keep these things in mind, that local flow will always be inclined, and now it has been reduced by induced angle of attack, that is alpha I, and finally now the effective angle of attack is denoted by alpha EFF. Okay, so there is a method that to calculate how you can find the induced angle of attack. Alright, so that we will be discussing. So that we actually will be discussing in the next class. Alright, thank you.